Hey class, welcome to a little home help for the first homework assignment. And we're going to get all the help we need to get everyone started during the year. And if we need to take an extra day to go over the summer homework, we'll do that. But make sure you watch this little video here and the other videos for the other homeworks and get done what you can and bring your questions with you the first day of school and we will get it all finished up. So let's pull up a new window here. That'll be fine. And I'm going to jot down a few equations that we're going to be using for the first homework assignment. It's pretty some basic stuff there. So we're going to be using some, ooh, there's a thick font. Hang on a second. There we go. We're going to be using some Pythagorean theorem, a squared plus b squared equals c squared. We're using some sides of a triangle with right triangle geometry, just to remind you. So if this is an angle, in geometry you may have marked it A. In physics we usually mark it with a Greek T or a theta. Okay, and this side over here is our opposite side. This side is adjacent, and this side is hypotenuse. There is three quick little functions we use from trig for right triangles that are helpful here. One of them is that the sine of the angle is just a number in the calculator, and it equals the ratio of however long the opposite side is divided by the length of the hypotenuse. Okay, and cosine is another function. You can use it in your calculator. You can use it in your phone if you turn to landscape view. And cosine of this angle compares two other sides. It compares the adjacent to the hypotenuse. Quick note here, hypotenuse is the longest side of the triangle, so by putting hypotenuse down here in the denominator for each of those two functions, it forces both sine and cosine can never exceed 1 or negative 1. Okay, so they kind of range back and forth between that. The third function is tangent, and tangent of an angle involves the two sides of opposite and adjacent. All right, since you never know which one's going to be bigger, the opposite or the adjacent, we're not going to be able to say whether or not tangent's more than 1 or less than 1. Okay, if you remember the graph of it, tangent actually blows up at pi over 2 or negative pi over 2 radians as the angle. Okay, because that forces the adjacent side to be approximately 0. One more quick note, if we're looking for an angle, we usually will do an inverse tangent or a second tangent or sine or cosine. So that looks like this in the calculator or your cell phone. And then you plug in the two sides of the triangle. For tangent, it would be opposite over adjacent, right? And for sine, it would be opposite over hypotenuse, cosine adjacent over hypotenuse. But if you do this, it gives you the inverse of a function like so, okay? Also, we want to look at a couple of other basic physics formulas of motion that you may or may not remember, and that's okay if you don't. I am going to take a small risk here and do a touch of calculus. And so if you haven't had calculus yet, because you're in BC, don't sweat it. Actually, let me erase. I don't like that. I just did. All right. So let me say that x as a function of t is equal to initial velocity times time plus 1/2 a t squared. And this is a formula that we get from kinematics or motion in physics. We'll explain and kind of explore again in class where this comes from once we get into it. But if we take the derivative of this once with respect to time, the derivative of position is velocity. That is, dx dt is our velocity. Okay, vi is a constant. T here is to the first power. When we take the derivative, we're left with vi, or vi times t to the 0 power. And of course, ti, anything to the 0 power is 1. So it's just an initial velocity is left. Over here, we're going to bring the 2 down, and we'll put the 2 in front of the 1/2, because the 2 is our exponent on our t here. Okay, and we see the 2 and the 1/2 cancel each other out, and so we're left with a function of, I'll rewrite down below, that the velocity as a function of time is our initial velocity plus acceleration times time. From this point here, we can figure out what acceleration is, and I'm just going to subtract the VI from both sides. So I'll say V as a function of t minus VI is equal to AT. By dividing both sides by t, it cancels out on the right. On the left, we said the change in our velocity over change in time is the acceleration. This is one way to look at the equations. So I want to briefly highlight or look at what we are going to consider are really basic equations of kinematics. That's one of them. The derivative of it is another one. Again, if derivative is not something you're familiar with because you haven't had calculus yet, don't sweat it. But this is, we can call this number 1. We can call this number 2. We can call this one, which I'll rewrite here briefly, number 3. So to rewrite it a little bit neater, this is usually written as either change in velocity over change in time for a nice constant average velocity. It can also be written as dv dt. Okay, and so this would be a third one. It's kind of a definition of acceleration. And there is a fourth one that I'm not going to go into a great deal of detail as to where it comes from. I'm just going to say that if we solve number 2 for time and plug it into number 1, we get rid of the time variable and we can rearrange it and end up with an equation that looks like this. That v as a function of time squared equals our initial velocity squared plus 2 times our acceleration times this x, or I'm going to say delta x. It's often written as a delta x, but not always. It's just change in our position from where we started to where we ended. Okay. Sometimes you will see me in a formula or even in a book somewhere else refer to this term right here as velocity final. Okay, that it's not the velocity initial, but it's some other velocity at some other point in time, usually at the end of the problem, so we call it velocity final. All right, so these are the basic equations of kinematics that we're going to use to solve some problems in assignment number 1. So let's take a look at a couple of them and see how some different ones have worked. I'm trying to add in one more that's a little bit basic or common knowledge, or the definition of velocity, specifically some average or constant velocity. By putting a bar over it like this, I mean an average or a mean. Right? That's not a symbol you're familiar with from mathematics. It's okay. And we're going to say this is just going to be our change in our position over our change in time, and that's our velocity. A simple example of this would be if you run 20 miles in 1 hour. We say you ran 20 miles an hour, okay, which human beings do not typically run 20 miles an hour. Not for a whole hour anyway. They can keep it up for a fraction of a mile typically, but not for a whole hour. So this again just says our velocity average constant velocity is change in position over change in time. All right, so there's no accelerating in this model right here. Another way to see this equation is to go back to equation number 1 and just set the acceleration term equal to 0. Okay, if we do set the acceleration term right here equal to 0, then that whole term goes to 0, and we see that we just have our position equals initial velocity times time. All right, and I was probably a little bit cavalier and left off a constant over here, so let me drop that back in. In this first formula, I really should have inserted a constant right here, and the constant that I should have inserted was my initial position. So xi is kind of missing a plus xi on the end of that. I apologize. It's 0 95% of the time in physics, maybe even 98% of the time, and so we won't be using it probably today for the homework. But I don't want to leave it off the formula sheet completely. All right. let's go ahead and take a look at some of the problems briefly and take a look at how we will tackle some of this. The whole point of the homework is to help you refresh your memory from some basic things you learn in physics in the first year. And so some of it will be kind of crunching formulas that will not be typical for the entire course. A lot of the course focuses much more on deep conceptual understanding in labs, but we definitely will be crunching some problems here as we kind of refresh things. The first couple of problems are kind of straightforward. They kind of work with average velocity. That was the last formula we introduced, as well as can you read a graph? And I'm going to leave those to you. I'm going to jump in at number 6. Number 6 gives us some information here. And so specifically, we have a 11 meters per second. And if we kind of label that with what it is, it's going to be our initial velocity in the problem. We then have a 13-second time during which we're accelerating, and we have a 1.7 meters per second squared as our acceleration, and it asks what is the average speed of the car. So if we look at our formulas, we don't want to make this a random guessing, almost like a pin the tail on the donkey. So I want to pick the formula with good strategy. I want to think of the things that I'm given and look for a formula that matches. So if I come back and look again, I'm going to say this is VI. This is obviously time. This is acceleration. And it wants to know what is the average speed during the period. Key is the word average. Okay, and so it is looking for this simple, some kind of average constant speed during the period. And so there's more than one way to get that, and we will look at that now. Let me pop open a new page here on the end. And so we are working number, what is it, 6? Yes, it's number 6. All right, so again, I want to just make a note of my given variables and numbers. That was 11 meters per second, 13 seconds. If I remember right, 1.7 meters per second squared is my acceleration. Okay, the unknown in the problem is my average or constant velocity. Okay, I probably need more than one equation to get to the end of this problem. But if I look at the 3 variables that I'm given to start off with, if I consider I have A, and I have T, and I have VI, okay, I consider I have those. Then when I come back to the second document and I look, there's only one formula that's here on the page that has all 3 of those variables in it and is just missing a 4th, and it's number 2. So this one right here is the one we're going to use, okay, because I don't know the V, but I do know the VI right here, and I do know the A, and I do know the T. So I can find the V, okay? So let's come back over here and say that for an equation I want, the equation I'm going to start off with, because I can find it, is I'm going to have my final velocity at the end of the problem, end of the 11 seconds, 13 seconds, sorry. Again, sometimes I write this as a VT, or V as a function of time. Sometimes I just put it as V final, because it's kind of a boundary condition to our problem. Our problem ending at 13 seconds on somebody's stopwatch somewhere. Okay. And here we can go ahead and substitute into the problem. I'm kind of jotting off these words here on the left of kind of steps that we go through in a lot of problems as we solve them. And you'll see me do this a lot during the year as well. I use the same words over and over. I'm going to go ahead and put my units in here. You don't have to put your units in here all the time. But I can see that I have seconds in a numerator right here. Right there. And I also have seconds in a denominator, second square. So I cancel one of them out. Then I'm left with units of meters per second there. Okay, so now last step here, I'm going to solve it. And I'll have to pull out a calculator to do that. That's not what I meant to do. as we finish solving this problem right here, I got 33 meters per second is the final velocity. When I compare that with the initial velocity of 11, you can probably see what our average velocity is going to be. I also want to point out that the first letters here of the steps of given unknown equation, substitute and solve, form the word guess. And so even when we are blindly lost on a problem, we can always guess, because you can always do given unknown equation and try and start substituting and solving even if you have no idea what you're doing in a problem. Because if you can read it, you can identify the given, you can identify the unknown just from the words. You can take a stab at an equation by looking at what equations have the stuff that we have and the stuff that we might be looking for. And in this case, we had to do an intermediate step of finding the final velocity first before finding the average velocity. Okay, so one way to find an average velocity was to find the average of two numbers. Okay, so I could punch in like velocity 1 plus velocity 2 divided by 2, and that would be an average velocity. In this case, the two velocities I would be averaging would be this one and this one. This is not really a physics formula. This is just a math formula on how to find the mean of two numbers, right? And I get 22 meters per second, not squared, sorry. This 33 was a little bit rounded. I think it's 33.1, but that's all right. Another way to solve it is the formula we have in the previous page, is that velocity is equal to change in x over change in time. So if we wanted to do a longer process here, we could actually use our final velocity along with our initial velocity and acceleration. We could figure out exactly how far we had traveled, right? So we could do this kind of step here and use this kind of formula. Or we could use the other formula, this v final squared is v initial squared. I'm going to add in here the x initial, though it's going to be 0. That is, we're going to assume we started at a position of 0 when we're finding our change in x. It doesn't matter what we call this number when we do our change over here on the left. We're starting at the same answer there. So my change in my position is equal to 11 meters per second times the time, which is 13 seconds plus 1/2, 1.7 meters per second times 13 seconds squared. Okay, and 13 times 11 should be 143. Okay. And that's in meters, and the second term of 1/2 AT squared I got 144 if I round. Okay, or 143.65. So when I put these two together, I'm going to get 286 or 87 meters. Right? And when I divide this by the time, we get 22.1. Which is about what we expect, okay? Because it's the same answer we got before. So here's two different ways to do it. Since these formulas, that is the one right here that I originally used, and this formula right here, actually both come from the exact same formula. If you remember, as we were playing with formulas back on this previous page, that formula number 2 is just the derivative of formula number 1. So they come from the same basic relationship in physics. And so it shouldn't surprise us that you can use either one of them to get to the final answer, okay? And they relate together, of course, by the way, our position, our velocity, and our acceleration. All right, so that is two different ways to work number 6. And we will move on here. I'm going to skip 7 and look for something maybe a little bit more, a little bit different or challenging. So number 8 is not a particularly mathematically difficult problem. It comes in 2 parts. Part 1 is number 8. Part 2 is number 9. And this can be more of a vector problem here, more of a math and triangle problem. So it says a person walks at 17.2 degrees north of east for 3.4 kilometers. Another person walks due north, then due east. How far north would you walk, and how far east would you walk? So this is almost looking for our projections of a triangle. Okay, so I'm going to shift colors here a little bit as I shift numbers. So now we're on to 8 and 9. So very quickly, here is a little cardinal directions of north and east and south and west. And if we walk at an angle of 17.2 north of east, that means start on the east and head northward 17.2 degrees. And it wants to know if you take that 17.2 and you were to break it up into a triangle and see how much of it kind of projects onto the north axis and how much projects onto the east axis. This is sometimes words people use for this. Or if you were to break this into a components with a right triangle, like so, with a east and north sides to the triangle. And again, my 17.2 degree angle is here. So this is my opposite side, my adjacent side, and my hypotenuse. And so it forms a right triangle. You either can walk straight up and then over to the right, or you can go at this diagonal 3.4 kilometers and end up at the exact same place. So when I look at this, I see that I already have my hypotenuse is 3.4 kilometers. I have my angle at 17.2 degrees, and I'm looking for the other 2 sides of the triangle. This is, again, is a little bit of a geometry problem here that many of you probably solved in freshman or sophomore year. And I might use functions like sine of 17.2 degrees equals opposite over hypotenuse. Again, the hypotenuse is 3.4 kilometers. Sine of 17.2 has no units. It's just a unitless empirical or decimal number that just relates the length of the 2 sides as a ratio. So the kilometers in my 3.4 kilometer hypotenuse become the units in the final answer. Cosine of 17.2 degrees would give me the adjacent side because it's the only thing that I don't know. Because again, 3.4 kilometers is the hypotenuse. Okay, that's how you do 8 and 9. I will leave the last little math step to you to finish that up. Okay, number 10 is very similar, and 11. Number 12 and 13 is again very similar with a triangle. Okay, so we have some sort of a length where you are already east of your port. Okay, so I'll put a little star here for home, and you start out the problem over here, and you are 630 kilometers east. A lot of these questions here are almost like reading comprehension. Can I understand what it says? Then I get blown. Remember again, this is home. That's where you want to get. And this is where we start. And we get blown down 450 kilometers. So now all of a sudden we're down here. And so you see we have 2 sides of a right triangle. And it's going to ask us both the distance, how far to our port, and also what is the direction. So this is the how far. Okay, and for the direction, you could either find this angle right here, or you could also find this angle right here. Right? I would call this angle that I'm numbering number 1, I would call that west of north. And angle number 2, I would call north of west. They're obviously complementary angles, and they form a 90-degree angle. As 1 plus 2 must be 90 degrees. But you can use either angle you want in the problem. Forgive me, you cannot. It only wants north of east, not east of north. forgive me again, north of east. North of east is this angle. So it's going to ask you for 90 plus angle 1. Okay, it's going to be north of east because you have to start at east and go north from it. And so they're looking for that angle there. If that's not utterly clear to you, that's okay. That's not even a physics difficulty we're having here. It's more like a why on earth do math people define angles like that? And that's another story for another day. Okay, a couple other problems that are very similar. Number 15 is a little harder and involves an idea that you need to wrap your head around. So for number 15 here, we're going to have a building, okay, and there's a ball that is thrown horizontally off a building. Okay, so here is a person, and they have a ball, and it's going to throw off, and as you might expect, it'll kind of arc and make a parabola shape down to the ground, and it's going to land 67 meters horizontally from the point of release. That is, if it was to drop straight down, it would land right at the end of my arrow, but instead it lands 67 meters away. The building is 97 meters high. Okay. And what you can do with these numbers is you're going to find out something about its motion, and we're going to recall, if you will, from freshman year, that this is called a projectile problem because the ball tossed in the air is a projectile, and the path it traces out, we call its trajectory, if you recall. If those words are totally, utterly new to you, then don't worry about it, and we will pick them up in AP Physics this year. One other thing I want to remind you as a review is that the acceleration due to gravity is given a special symbol. The ball is falling downward because of gravity, and rather than putting an A for acceleration, we put a G because this is a special acceleration, and it has a numerical value in metric units of 9.8 meters per second squared. That means that every second the ball is falling, its downward vertical component of its velocity is changing by 9.8 meters per second every second. So maybe in the beginning, I'll change off my color here with my arrows. It has a speed going sideways like this. And then when it gets here, it still is going sideways with the same speed. That is, it's not going to slow down in its velocity to the right because there's no force acting on it to the left. If we kind of ignore air resistance, which this problem is going to ignore air resistance. But now it's heading downward a little bit. Okay, so if you want to find the velocity, I got to use Pythagorean theorem with my blue arrow and my green arrow together to figure out what its speed is. As it moves over here, its horizontal speed has not changed. It's the same, but its downward velocity is increasing. Okay, and as it gets closer to the ground, its horizontal velocity has not changed because there's nothing pushing or pulling it to the left or the right. But sure enough, its vertical velocity is getting longer. And so it's going faster and faster downward. So as you look and say, hey, I wonder how fast it is going here at the end, the answer is you got to know what both those velocities are. Because I'm looking for the hypotenuse of a triangle that is created by the blue and the green. Okay? So the same green line over there is over here forming a right triangle. And in Pythagorean theorem, we can find that. So let's go ahead and start to jump into this problem. And we're going to have to solve for a number of things. We're going to solve for, hey, what is this downward velocity right here? And we also are going to have to find, hey, what is this horizontal velocity right there? And then we'll do a little Pythagorean theorem to figure out what is the speed of the ball just before it strikes the ground. Okay. There's another way to solve this problem using energy and not using this stuff. We can use potential and kinetic energy stuff. And we can look at that solution for it also. So as I look at my solutions here, I'm actually going to want to talk for a second and very carefully define here that this is the equation I want to use for the horizontal motion. Okay, because the horizontal motion, again, was a constant velocity. It did not change the length of the arrow, which is what I was using to define how fast it goes. Right? Long arrows travel fast, short arrows were slow, and the blue arrows were the same length. So I'm going to use this kind of formula right here for my horizontal motion with a blue arrow. For the green, I want to use something that involves acceleration due to gravity. And so I'm going to use something more like this or something more like this. Okay, because I want to have something with the idea of that we are moving a certain vertical distance in a certain time because of a vertical acceleration, making the ball fall faster and faster downwards, even as it moves off to the right. And that's what forms that parabolic shape in that arc or trajectory. All right, so let's go ahead and start to work the problem a little bit and finish it up. What number was this on anyway? We were on 15. Okay. Okay, so here is 15. I'm going to switch inks just for visibility, but I'm going to solve the vertical part of the problem first. I'm going to jot down some given information. So my G with a colon stands for my given. I know that 97 meters is how high it fell. Okay, that's the distance, or what I use is delta x in my formula right here. Okay, it's my delta x. And I also know that it started out at a speed of 0 in the vertical direction only. So I know it was moving sideways when it was thrown, but it was thrown horizontally. So it wasn't thrown up into the air or down, it was thrown straight out. So I'm going to say that it didn't have any speed going up and down in the beginning. And I also know that for this vertical part of the problem, that the acceleration, the A in my equation, is going to be 9.8 meters per second squared. So as I plug into this equation, I know this is delta x, but we're using it for the y-axis. And that's something you'll have to get used to in physics, is that we use variables like x. They don't always mean horizontal. They could mean x, y, or z-axis. They just mean a change in my position, change in my distance. We call that a displacement in physics. And we don't need to use that word too much at the moment. But here is the formula that we plug into. And there is something in this formula that we don't know, and that would be time. All right, this isn't the way we have to work the problem, but this is the way a lot of people work problems with projectiles. So as I start to plug in 97 meters, that's how far the ball moved straight down. If we had dropped from the top to the bottom of the building, that's how far it moved down. I'm going to put in a 0 right here, times t, which will all be 0, because 0 times t is 0. Again, this initial velocity, I'm only concerned with the y stuff in this equation of the problem, because the y stuff is the vertical information and it's independent of my horizontal motion. Another way of saying independent of the motion is that gravity down, I'll bounce back to the problem here, the gravity downward had no effect on the blue arrow. So I don't want to use any information about the horizontal in my equation because the vertical information was independent. Okay. This is probably the most advanced problem in this problem set. And if you didn't do projectiles when you were in 9th grade, then this is like completely new information. And don't let it blow you away. This is why I'm doing it for you. I mean, with you, of course, so that you can have something to work with to get your homework done. And the time I don't know, but this is one equation and one unknown, and we can solve this, okay? So if we take that 97 meter height right there, and we move our 1/2 and 9.8 from the right-hand side to the left, find out the time squared is about 20, or 19.8. All right, and the square root of that is 4.45. So 4.45 seconds is equal to the time the ball was in the air. Now that's very useful for us because that gives us the time for both directions, the vertical and the horizontal. And I almost out of room here, so I feel kind of silly. I'm getting crowded. All right, and so I'm going to quickly work a couple problems here. Let's look at the blue, the horizontal, really quick, and then we'll look at the vertical again and see what our green line should be. So our vertical speed should be our change in distance, 67 meters, divided by how long the ball was in the air, which is 4.45 seconds. Okay, and that is going to be 15 meters per second. The ball was thrown horizontally. Okay, let me shift off to green here and pick a darker green. We can see this. So my velocity in the y direction would be my initial velocity in the y direction. We'll call that 0, please, plus acceleration times time. So when I multiply the 9.8 acceleration times the 4.45 seconds the ball was in the air, I'm going to get 44.1 meters per second. So now to solve the problem, I'm going to jump back to this page here with the homework. I have 44.1 meters per second, and then for the other one here, we had 15 meters per second. The red's actually what I want to know. It's the hypotenuse of the two, and so that's going to be like the c squared in my Pythagorean theorem. So I'm going to do 44.1 squared plus 15 squared, and then I will square root that to find out what is the speed right there of it at the beginning. And I'm getting 46.6 is the hypotenuse. Okay, if you're not getting that, if you're getting a number over 2,000, make sure you take the square root. And so that is how fast it's going. All right. So this has been a quick little overview through the first homework set. I'm going to put up some other videos for homework sets 2, 3, 4, 5. Please give them a look. And we started out kind of basic here. And if you don't remember anything from this entire unit whatsoever, and you're like, I'm a blank slate in physics, don't sweat it. And we're going to be covering all this as we go through class and looking at it more deeply. But I just want to make sure we start with some common vocabulary and common experiences that we discussed. And that's kind of the whole point of the summer homework, is to familiarize yourself with some of this. All right. So watch the other videos, and please feel free to contact me via email, dbrown@parishepiscopal.org, or also you can contact me, but just coming by school anytime, August 17th or later, and just catching me in some afternoon after the meetings are finished, and I'll be happy to work with you on your homework. And other than that, have an awesome end to your summer.